Okay, good morning, everyone. Welcome to today's presentation on the HYDEA project. As Yarima, my colleague said, I'm Joaquín, and I'm a part of the Energy Lab, the technologies researcher team. And today I'll be discussing with you the crucial role of green hydrogen in reducing carbon emissions in ports, particularly in the Atlantic region. So with this presentation, we cover several areas, key areas. For example, the importance of decarbonizing the ports, the available technologies for green hydrogen productions, the specific strategies for implementing these technologies, and the challenge that we face and the potential solutions to overcome those challenges. So this comprehensive approach aims to provide a clear understanding in how green hydrogen can revolutionize port operations and contribute to a sustainable future. So as Yarima said, also the HYDEA project focuses on identifying just to clarify, this is part of the work that we've been doing in work package number 4, called Identification of Opportunity in HYDEA Ports. The project focuses on identifying and implementing sustainable energy solutions to decarbonize ports in the Atlantic region, and by promoting the adoption of green hydrogen, the project aims to reduce carbon emissions and improve air quality and enhance overall sustainability of whole ports operations. Okay. Okay, so the first topic we will cover is the role of hydrogen in decarbonization, and the natural questions that arise, for example, is why ports, and why improving and support the decarbonization through the incorporation of hydrogen technologies in ports. Well, ports are crucial to global trade, handling, and significant portion of the world goods. And however, as you may know, they are also substantial sources of greenhouse gas emissions due to the heavy reliance on fossil fuels for operations, transportation, and associated industries. So decarbonizing ports is vital to reducing that global carbon footprints and to fight against the climate change. The ports are expected to play a key role as energy transit hubs, facilitating the import of hydrogen and subsequent transportation to multiple end users. The data collected here is from, I think it's a Deloitte report that from the Clean Hydrogen partnership that say that up to 42%, about 22 megatons of total hydrogen demand in Europe in 2015 could be located in port areas. So these are here you can see in the slide 3 of the main objectives of the HYDEA port of the HYDEA project. The focus on identifying and implementing sustainable energy solutions to decarbonize ports in the Atlantic region, to promote and adopt the green hydrogen, and we'll talk about this in a few minutes about what is green hydrogen and why it's so important. Technologies to enhance overall sustainability, and the promotion and integration with renewable energy sources and foster collaborations among regional stakeholders. Okay, so we must talk about, of course, what is the two dominant types of hydrogen for decarbonization. And we have here in the slide at the left the blue hydrogen production, and at the right the green hydrogen production. And basically the blue hydrogen route implies the chemical reaction through steam reform process between methane and water, and this is basically the same process that takes place in the gray hydrogen synthesis, but incorporating or adding to the process the carbon capture and storage. And on the right, we have the green hydrogen route that implies when also called renewable hydrogen, because it utilizes 100% renewable sources. And technological devices called electrolyzers that produce, those are responsible to convert water into green hydrogen and oxygen. We'll talk about later about these technologies. I want to waste your time because I know that Professor Aurelio will talk about more deep about these aspects. So, which are another question that another topic we must talk about is the strategies to decarbonize the production of hydrogen. And as we mentioned before, the green hydrogen production utilizes only renewable sources, and integrating renewable energy sources is key to hydrogen production. Offshore wind farms, for example, especially in the Atlantic region, provide a consistent and a robust energy supply, ideal for electrolysis. The proximity to ports minimizes the transmission losses and infrastructure needs for hydrogen transportation. Of course, offshore wind farms in the Atlantic region and high capacity factors making them suitable to continuous hydrogen production. The second one is the solar energy, another vital source. Solar photovoltaic panels can be installed in port areas, for example, on rooftops and even on floating platforms, as we can see at the figure, to generate electricity for hydrogen production. Solar energy can complement, in this context, can complement wind energy, ensuring a steady electricity flow. Combining this source in hybrid systems ensures a continuous supply of electricity for hydrogen production, even when one source is less available. So considering these two strategies, we also must talk about the integration methods that we can see in the port areas. And we can identify two integration methods: the on-site installations and the hydrogen transportation route. Regarding the on-site installation, setting up a hydrogen production facilities directly within the port areas are significantly reduce the transportation costs and enhance operational efficiency. So on-site installations allowed immediate use of hydrogen for port operations, such as refueling machinery and vehicles. On the other hand, hydrogen transportation, when the on-site production is not feasible, hydrogen can be produced in centralized facilities and transport them through pipelines, for example, to the using area. And this requires actually a significant investment in hydrogen storage and encouraging infrastructure, and the establishment of hydrogen refuel stations that involves new technology that are being developed at the moment. Okay, so it is impossible not to talk about green hydrogen production technologies. So this slide wants to overview the process in which water is converted into hydrogen and oxygen through electrochemical route, through an electrochemical process that takes place in electrodes in these devices called electrolyzer cells. There are different technologies, as you may see in the slide, the outline, the proton exchange membrane electrolyzer cells and the solid oxide electrolyzer cells. There are different between each other regarding to mature technologies. For example, alkaline electrolyzer cells are mature technology with relatively low cost but lower efficiency compared with the newer methods. And when I'm referred for newer methods, I'm talking about proton sheet membrane and solid electrolytes. The PEM offers higher efficiency, for example, but and flexibility, but with higher costs and maintenance. The solid oxide electrolyzer cells are of those systems that one who has the higher efficiency and the ability. Maybe the ability is not the correct word to use here, but because there is a necessity to operate at high temperatures, because diffusion process as ionic diffusion needs high temperatures. So the need to operate at these high temperatures has an advantage because it's suitable for industrial integration. And the identified challenge that as the result of this research conducted by Energy Lab in interviews conducted with the port authorities, for example, in the Spanish region, specifically the Port of Vigo and Port of Sevilla, are the initial costs, the technological barriers, regulations, and last but not least, the social acceptance of these technologies. And ongoing, for example, for the initial cost, the high capital expenditure for setting up electrolyzer plants, renewable energy infrastructure, and hydro storage and distribution network could be a significant barrier. Regarding the technological barriers, the need of improvement in electrolyzers, the durability, the cost reduction. As you may know, these technologies uses critical raw materials. The prices of palladium, nickel, iridium are very high to make hydrogen production competitive against traditional fossil fuels. Complex regulatory landscape for hydrogen production, the storage and distribution, the requiring of compliance with safety and environmental standards, the public perception and acceptance of new technologies and infrastructure developments are crucial for successful identifications. So we can, as we identify the challenge to overcome, there are potential solutions identified for each topic. For example, for technological innovation, the ongoing research and development efforts, and to enhance electrolyte efficiency, reduce cost, and improve overall performance. Advancing material science, engineering, and process optimizations are key factors to overcome these barriers. Financing models, the public-private partnerships, government incentives, for example, tax incentives, and innovative financing mechanisms can help to attract investment and reduce the capital costs for that investment. Supportive policies, advocacy for policy that facilitates hydrogen infrastructure development, such as streamlined permitting processes, standardized regulations, and incentives for renewable energy integration can accelerate the adoption of these technologies and green hydrogen production. Also the public engagement, the creation of educational campaigns, stakeholder consultations, and transparent communication about benefits and safety of hydrogen technologies can build a public trust, and acceptance. And the next slide, we have some of the results of the information collected from the interviews that will be conducted with the port of, as I mentioned before, the port of Vigo and the port of Sevilla. For example, the port of Vigo, regarding to hydrogen generation, storage, and distribution, is working on the Julio Verne investment project to produce green hydrogen from photovoltaics, and infrastructure hydrogen distribution station will be constructed outside of the port, of the area port, and potential opportunities identified from this forward regarding to the mobility, dumpers, cars, and heavy road transport substitution that, of course, utilizes conventional fossil fuels with consume hydrogen from the port, the generation and distribution, photovoltaics and electrolysis, and in final uses, the green methanol. Sorry, there's a H missing in methanol. And use of as a novel fuel in this case. For the Port of Sevilla, this is a different infrastructure. Is an inland port. General features are different, and different opportunities was identified. Hydrogen generation, storage, and distribution. There are two projects ongoing: the Allen in this hydrogen and ammonia production, respectively, and the potential opportunities identified as the similar to Port of Vigo, the mobility. The Port of Sevilla has a terminal, container terminal that operates with merchant transport, trains and heavy road transport, dockside and mobile cranes, and again, green methanol and ammonia reconversion was identified as opportunities of final uses in the hydrogen chain value. And like for the final reflection, why hydrogen, green hydrogen production for the future? That's the final questions that we must ask ourselves. Well, environmental benefits, growth, economics, and sustainable future. The long-term impact includes these three aspects: significant reduction in carbon emissions from port operations, and associated industry will contribute to global efforts to fight against the climate change and improve air quality in port cities. Regarding to the economic growth, the development of a green hydrogen economy will create new industry and job opportunities and stimulate innovation and attract investment in renewable energy infrastructure for sure. Energy, green hydrogen provides a sustainable and versatile energy carrier that can enhance security by diversifying energy sources and reducing the dependence on fossil fuels. And by decarbonizing ports and key sectors like transportation and industry, we can transition to a more sustainable energy system.